This is Neil Patwari. In this segment of ESE 471, I'm going to talk about drawing the line between two symbols. How to draw the decision regions between two symbols in a k greater than or equal to 2 space. Okay, so I draw two symbols, here Si and Sj, and I want to know what is the region of X that would make me decide that symbol I was sent. And what is the region of space that would make me decide that symbol J was sent? And last time we talked about how the optimal decision is to pick the symbol I that minimizes the distance between X and Si. So we'll decide Si if the distance from Si is less than the distance from Sj. What we're going to do in this segment is we're going to talk about what is the region? Not just for any arbitrary x. I can pick an x and I can say, oh, well, this distance is shorter than this distance. I want the set of all points x such that the distance to Si is smaller than the distance to Sj. Okay, so let's find that set of points. And the first thing we're going to do is we're going to replace this with an equality. We're going to talk about x minus Si being equal to x minus Sj. If I can find this locus of points that makes this statement true, that becomes the dividing line, the border between Si and Sj. And also we're going to square both sides because it ends up it's easier to work with squared distance than the square root of the squared distance. That is, this expression is an inner product of the vector multiplied by itself. And I can solve this. I can use FOIL, first, outside, inside, last, to multiply out each side. And when I do that, I can cancel out the x squared terms. I can group together these terms. These terms are the same because it's an inner product. It gives me one number. It doesn't matter which order it's in. These are the same. And so I'm going to group them together. What I'm going to do is I'm going to try to make this look more like the equation of a line, as I have a function of x and a constants on the other side. And I'm going to divide both sides by 2. And this becomes my expression for essentially the equation of a line that separates these two regions, the decision region for Si and the decision region for Sj. But this is still a rather complicated equation. So what I'm going to do is I'm going to argue that it doesn't really matter how I draw my coordinate system here. I'm just trying to draw a coordinate system that allows me to draw the line of x. If I draw the line of x in that new coordinate system, it doesn't really matter if I had translated or rotated the coordinate system to make it easier for me to understand what that line should be. So in this case, what I'm going to do is I'm going to draw one axis that includes Si and Sj in it. When I have two dimensions, I have to draw a perpendicular coordinate. I'm going to pick this second coordinate axis so that the perpendicular line is exactly halfway in between Si and Sj. So on my axis 1 here, I've got Si and Sj lying on those lines. This axis is perpendicular with the origin halfway in between Si and Sj. So when the origin is halfway in between them, these two become equal, so they cancel each other out. And in this new coordinate system, I get Sj minus Si transpose x is equal to 0. This difference between the two vectors, Si and Sj, inner product with x equals 0. Well, what is that? Where do I get the x inner product equal to be 0 in this coordinate system? Well, it turns out this is a projection of x onto the y-axis, onto this new y-axis over here. And that means that I can pick any point that's perpendicular to that axis, starting at the origin and working my way perpendicularly away from that point. So this axis becomes the region of x. X on this line makes that distance equal. between SI and SJ. And you can see that that's true on this perpendicular bisector. So this equation says to pick x anywhere on a line that is perpendicular to this axis. And if it wasn't 2 dimensions, for example, if I had a 3-dimensional plot, I would have another axis coming out of the board here that would then allow me to pick any point on a plane that is perpendicular to this line between SI and SJ. And if I had an arbitrary k-dimensional subspace, then I would have a k-1 dimensional subspace. K-1 dimensional subspace is a line in k equals 2, a plane in k equals 3, and generally we would just call it a k-1 dimensional subspace when k is greater than 3. The short story is that the criterion that we need in order to have this expression met is that we draw a line that is a perpendicular bisector of the line between SI and SJ. And the points where I would decide SI are all on the side of that line that is closer to SI than to SJ. So the line actually splits our space into 2. So let's talk about steps here. We draw a line segment connecting SI and SJ. Then we draw a point in the middle of that line segment. And we draw the perpendicular line to the line segment through the midpoint. And that's it. That's how we separate region J from region I.